move on. Yes. Okay, put your hand up and wave it around if you want to. Mike will stop talking. That's what I thought. Okay. So now if you take Boyle's law, which is pressure and volume, and Charles' law, which is temperature and volume, and you squish them together, what you get is called the combined gas law. And it's P1 V1 over T1 equals a constant equals P2 V2 over T2. And yeah, I did leave one relationship out. It's the pressure-temperature relationship. That's called Guy-Lussac's law. If you're really interested in it, you could probably figure it out, but it has the same setup as Charles' law. So we can use the combined law when everything changes, when everything but the amount changes. When both the pressure, the volume, and the temperature can all change, we can use the combined law. And then the last, or the next law, will show what happens if the actual amount of gas changes. That's called the ideal gas law. Constant. So frequently the constants just dropped, but yeah, so the combined gas law is this. P1 V1 over T1 equals a constant. But textbooks usually show it like this. P1 V1 over T1 equals P2 V2 over T2. It's some number. Just it basically means these three things, their product or their quotient is a constant.
So that number becomes that constant.
Question? No. Okay. All right. So what this means is you can have things that change in opposition to each other. You can have a pressure which would make the volume go up, and a temperature which makes the volume go down, and you can't really predict what's going to change without doing the math. The good news is there's a big fat equal sign in the middle, so you can always check your work. Are we ready to go for it?
Yes.
All right. Consider this scenario. A sample of gas at 2.3 atmospheres, 3.2 liters, and 310 Kelvin. What pressure will that gas exert if we change the volume, increase the volume to 4.1 liters, and increase the temperature to 500 Kelvin?
It's going to go up. It's going to go down.
Now, ladies and gentlemen, once again, you got an equal sign in there. That means you can, when you have an answer, you can multiply that by that, divide by that, and write it down. And then multiply that by that, divide by that, and write it down. And those two answers should be the same. So you can check your work. You're not married to whatever the calculator spits out on the first try.
Please stop being a
I take it from the chatter that you're ready to move on?
Yes.
All right, so you got something going on here, guys. You have an increase. You have an increase in volume, which would seem to suggest that the pressure went down. But you also have an increase in temperature, which would seem to suggest the pressure went up. So what did the pressure do? What's P2?
I got
2.895.
2.99.
2.9 atmospheres. So the pressure actually went up. Question. Okay, guys. The question was, how do you solve this? And the answer is, take your formula, V1 over T1 equals P2 over T2, and then plug in your relevant values from your exercise. This does require you to read the exercise and decode it. A sample of gas at 2.3 atmospheres, 3.2 liters, 310 Kelvin. What pressure, P2, will it exert at 4.1 liters and 500 Kelvin? Once you're here, and you filled this out, you choose whichever math technique you like the best. What I would do is I would find out what this whole number is, and then I would multiply it by 500 to get rid of the denominator, and divide it by 4.1 to get rid of the numerator. But that's just me. Some of you are going to be like, I like to make big, huge formulas. So 2.3 multiplied by 3.2 multiplied by 500 divided by 310 multiplied by 4.1. That's going to give you P2. I'm not really that kind of guy, but if that's the way you want to do it, that's fine. The important thing is you have a denominator on your variable side, multiply both sides to get rid of it. You have a numerator on your variable side, divide both sides to get rid of it. Capiche? Okay, you want to do one more or call it a day?
Do one more.
Do one more, okay.
Wait, what?
I like the cut of your jib. All right. A sample of gas at 1.8 atmospheres, 0.56 liters, and 290 Kelvin. What volume will it occupy at STP?
Standard temperature is 273.
What?
Instead of the cycle, it just smashes his head. Scotty should I went to get the rebound. Just probably all purpose lay down.
Oh, I see.
Remember, you got an equal sign in there so you can check your work.
I've got.
You got this, brother.
Oh, I got 2.95.
You can do this, brother.
I had the best gumbos. Dude, why did you invite me over?
Yeah.
0.949. I'm talking to him.
You know we're like that. No, you don't know the He's like, funny.
So if you realize SDP is 1 atmosphere and 273 Kelvin, then you're halfway there. If you were like, it doesn't give us a volume and a temperature and a pressure, then you're probably off. You need to realize SDP is 1 atmosphere, 273 Kelvin. So when you do that, what's the new volume?
0.95 liters.
0.95 liters. Okay, cool. We'll practice these again tomorrow in a worksheet environment.